a nice power of two number of participants, so that's a good place to get going. So good morning or afternoon or evening to everybody out there. We're resuming the Theory to Practice Lattices workshop, and our first talk today is by Thomas Perez from PQ Shield. He'll be telling us about fast algorithms for doing Gaussian sampling and structured polynomial lattice. Afternoon or evening to everybody out there. We're resuming the There we go. Okay, I'll take it away, Thomas.
Thank you for. Can you hear me?
Yes, we hear you great.
So there was some
perfect
echo before, but
okay. So thanks for the introduction and thanks for the invitation. So in this presentation, I'm going to talk applications. So I will start by a bit of motivation, and a common motivation for this talk, as well as the talk of Thomas Pornin, which will be the next talk, and the talk of Alexandre Wallet, which will be the talk after that. So common point for all this common motivation are over and through lattices. So as a small reminder, so GPV signatures are signatures, hash-dense sign signatures over lattices introduced by Gentry, Peikert, and by Catanata. And in the vanilla version of GPV signature, because you have a twig by Mitchell and Peikert, but I'm not going to talk about this version. I'm going to talk about the most classical. So in these two matrices A and B, such that B times A is equal to 0, such that B efficient. And the public key will be the matrix A, and the private key will be the matrix B, which will be a trapdoor. And then in the signing procedure, the idea is that you will hash, so it will be a hash and sign signature to hash your message into a target C. And then you're going to use a trapdoor, what is called as a trapdoor sampler. And I will explain later what exactly is going on with the trapdoor sampler. So we are going to use this trapdoor sampler to generate a vector in the lattice generated by B, and it should be two. So this is illustrated in the example on the right. So you have your target C, and you have your point V, which belongs to the intersection of the lattice and the Gaussian and the support of a Gaussian centered on C, and the signature will be the difference between C and V. And the verification procedure consists of checking that we have two conditions. So first, S should be short, and second, we should have S time A equal to the hash of the message. So in my talk, I'm going to focus on the step 2 of the signing procedure. And I will focus on how to do this step as efficiently as possible and also in a secure manner. Then the talk of Thomas Pornin will be on the step 1 of keygen. So how to generate more precisely the special form. It will be the generating the basis of an n-true lattice. And finally, Alexandre talk will be a bit more global because he will talk about what happens with true lattices by module and true lattices, and so he is going to have a more global view and talk about the whole enchilada. All right, so the focus of this talk is, like I said, the step 2 of the signing procedure. See how can we efficiently and securely compute a vector V in the lattice generated by B. So vector V close to the target C. And this talk will be roughly in 2 parts. So the first part will be purely algorithmic and algebraic. It's called fast Fourier orthogonalization is Duca, so the entire section is the joint work. And the second part will start from this algorithm, which we will show is efficient, but in the part one, we will not study at all the security of this algorithm, only its efficiency. And so in the part two, we will study the security and see how go validation to fast Fourier sampling. And the section two is an amalgamation of work with the faculty and also work that I did alone. And it will use statistical arguments and more precisely the Renyi divergence. Okay, so first, so before going into the details, I will have to provide a bit of definitions. So the Gram-Schmidt orthogonalization, or GSO, takes as input matrix B, full rank matrix B, and will compute the factorization in equation one, which is writing B equal to the product of matrix L. Matrix, the condition is that L should be lower triangular with ones on diagonal, and B should have orthogonal rows. And there are many algorithms which allow to do that in times the big O of Mn square. On the other hand, we have the LDL decomposition, which takes as input a matrix matrix coefficients, a square matrix, which should be self-adjoint, which means that its conjugate transpose should be equal to itself. And the goal of the LDL decomposition is to compute the factorization G equal L times D. L should be again lower triangular with ones on the diagonal, and D should be diagonal. And there exists algorithm which can do that in times big O of n to the cube. So the algorithm that I will present in this section, it uses 3 facts, and 2 of them are explained. So the first fun fact that we will leverage is that when G is equal to B times B star, the GS equation 1 and equation 2, the matrix L in the 2 equations are going to be the same. And for us, that's interesting because the Gram-Schmidt orthogonalization, it takes time big O of Mn square, and the LDL decomposition, it takes time big O of n cube. So whenever M is going to be larger than n, it makes more sense from an efficiency point of view to take the LDL decomposition. And this is what is going to happen in our algorithm. So in our algorithm, it will make sense to consider decomposition, which is fine because both are equivalent anyways. So that's for the fun fact number 1. For the fact number 2, the GSO and LDL, they generalize to ring and fields of the form phi or some polynomial phi. So in order to do that, you have to provide adequate generalization of the adjoint or the complex conjugate, and generalization of the inner product. And it's easy but tedious to show that once you have these adequate definitions, you can just take the regular algorithms for doing the GSO and or the LDL, and you general algorithm. Okay, efficiently a closed vector. So the 2 most famous algorithms to do that efficiently are were formalized by Babai, even though they did exist before. So it's the round-off algorithm and the nearest plane algorithm. So the round-off algorithm is your target phi, and you express it in the, instead of expressing it in the canonical basis, you will express it in the basis B. So for doing that, multiplied by vectors in row notation. And so the lattice generated by a matrix, it's the lattice generated by the rows of this matrix. Okay, so we take this representation, we obtain a vector t, and then what we are going to do is simply we round all the vectors b, which is in the lattice. Okay, so
Thomas?
Yeah.
Thomas?
Yeah.
The many participants are getting very garbled audio. I'm not sure if is your connection using any any network other than the Zoom. I think the video is important for people to be able to see, but I'm not sure. Is there anything you can do on your end to?
Yeah, I'm trying to disconnect everything that's unrelated to the talk.
And actually,
is it better now?
Yeah, slightly better.
Yeah, it goes in and out. I mean, it's good for a while, and then it gets garbled, and then it's good for a while.
And Chris, if if that doesn't work, maybe he can turn off his video, but just do the screen share. That's sort of a next step.
How do you mean the screen share without? Wouldn't we need to be able to see his slides?
Yeah, screen share, yes, but not his video.
His own face video. Okay.
Yes, that's a next step in some sense.
Okay, hopefully now it should be better. Let me know if it's still garbled.
Thomas, you might want to turn off your video of yourself, and then we'll just have the screen share and your voice. That would probably help.
Mm-hmm. Yeah. All right. Yeah, let me know if it's still if I can do anything else.
Okay, it's pretty good now. Let's hope it stays.
And yeah, by the way, my talk is originally scheduled for 1 hour and a half, but it should be closer to 1 hour. If you have any question or comment, feel free to ask them. So I cannot see the chat, so someone will have to ask me on audio. So coming back to the round-off and nearest plane algorithm. Okay, so that's the description for the round-off algorithm. And for the nearest plane algorithm, the description the same, and the only difference is the section of code that I have highlighted in the orange box. So instead of rounding each coefficient tj in parallel, relatively. And by this, I mean that before rounding tj, you take into account all the previous ti that you rounded before, and you take them into account as well as the DLDL decomposition and depth. And but other than that, the two algorithms are exactly the same. And we can see on the right picture, then you get a different result than on the left picture. So the round-off algorithm, you can show that the point that's going to be output by the algorithm is at the intersection of the lattice and of a parallelepiped having the form of the basis. And this parallelepiped will be centered. In case of the nearest plane algorithm, it's the same. So you have the intersection of a parallelepiped and of this time the diode will not have the form of the basis, but it will have the form of the orthogonalized basis. And other than that, the two parallelepipeds have the same volume. So, so one can show that on average and in the worst case, the nearest plane algorithm will give you okay, but than it is for the. Okay, so now let's try features of wing, which is R, and phi can be many types of polynomials.
Thomas,
So it can be a convolution.
Thomas, Thomas, can you hear me?
Yes, and you?
We haven't heard any audio for about the past 45 seconds. Is it possible, are you on a mobile device? Is your connection strong? Is it just a matter of bandwidth?
Yeah, I'm at my place, so I'm sorry, I don't know what I can do to make that faster.
Okay.
Come on, maybe you can move to a different location in your place. Is there somewhere that the connection is stronger, maybe?
I'm already as close as possible from my box.
Mm-hmm.
So, okay, let me try to deactivate my remote mouse. Maybe that will be better. Okay, can you hear me now?
Yeah, we hear you pretty well. Could you repeat the last minute or so of what you said in your talk?
Yeah, sure. I'm sorry, I apologize for all the technical issues. Okay, so did you follow the end of that?
I think we heard up to the point where you were describing the rectangular parallel pipette for nearest plane.
Yeah, so what I was saying is that in the case of the two algorithm, you will get similar outputs in the sense that you get an output which is the intersection of the lattice and of a parallelepiped. And in both cases, the parallelepiped will have the same volume. But in the case of the round-off algorithm, the parallelepiped will have the form of the basis. And in the case of the nearest plane algorithm, it will have the form of the orthogonalized basis. And we can show that the nearest plane algorithm will will give better quality output in the sense that it will give you closer outputs. So it will give you closer outputs on the average and also in the worst case. And so the nearest plane algorithm is more desirable for cryptography. But unfortunately, and this is what I will discuss in the rest of the talk, it's harder to accelerate it over ring lattices. And yeah, this is what I will talk about in the next slide. Okay, so it's common to take, in cryptography, it's common to take matrices and vectors with coefficient in a ring. So ZQX represented by phi. And phi can be a convolution polynomial, x to the n minus 1. And this was the case, this was done by the original n-true schemes, if I remember correctly. You can also take a cyclotomic polynomial, and the most prevalent example is taking the cyclotomic polynomial x to the n plus 1 for n to the power of 2. And you can also take another polynomial, such as, for example, x to the p minus x minus 1, as is done in n-true prime, for example. And so the techniques that I describe here, they do provide speedups for subsets of 1 and 2. So they provide speedups whenever we are in tower of rings, but they do not provide speedups for the case number 3 because it's not, it doesn't have a tower of rings structure. And this is by design, by the way. The n-true prime designers, they chose this polynomial on purpose. So yeah, there doesn't seem to be at least a straightforward way to apply them for such polynomials, but it's an interesting question to see in the future if it can be done. Okay, so I'm going to focus on phi equal x to the n plus 1 with n equal 2 to the kappa. And I will note kn equal qx quotiented by xn plus 1. which is a cyclotomic field. Okay, so our goal is to provide a faster nearest plane algorithm over tower of rings. So this will be done in 2 steps. So the first step is to provide a compact representation of the orthogonalization of a matrix. And then we will see how to use this compact representation in order to provide a faster nearest plane algorithm. And so this algorithm allows to have a nearest plane algorithm which runs in times big O of n log n. And then we will see that we won't see that, but we can generalize them to module lattices with base ring, a tower of rings. And in this case, we will have something which is quadratic in the rank of the module lattice. Okay, so if there is no obvious way to exploit the ring structure, what one can do is to map everything to Z. So for example, if we consider the ring endomorphism, which to a polynomial Gx, an element of K4 maps G multiplied by A plus Bx plus Cx squared plus Dx cube. So this can be interpreted as the endomorphism of Q to the 4 with the associated matrix over the canonical basis 1, x squared, x to the cube, which is the matrix on this figure. So this is an anti-circulant matrix. So the problem with doing that is that the power basis is not adequate for the GSO or the LDL. So in the example that we take, when we have the matrix B, it has a nice anti-circulant structure. But when we compute the Gram-Schmidt orthogonalization, then the matrix L and the matrix B tilde, they are not anti-circulant at all, and they don't have any obvious structure. And so, for example, it's not obvious that there is an efficient way to store L in times in storage big O of n. And since there is no obvious compact representation, and it seems at first sight that we need space big O of n squared to store L. Well, since this matrix L is going to be used in the nearest plane algorithm, if you need all n square coefficients, then it doesn't seem obvious at first that you can do better than big O of n square complexity. And this is unsatisfying because if you look at algorithms such as the round-off algorithm, well, the round-off algorithm is very amenable to the ring structure. And for the round-off algorithm, you can get a complexity big O of n log n. So our goal will be to find a better representation. And this is what I will talk about in the next slide. So the first observation is that if we represent T, instead of taking the canonical basis, we will take we'll take the canonical basis, but in a different order. So in the order 1, x squared, x to the cube. It will give us the transformation matrix in equation 3. And this is quite interesting because we get a matrix which is no longer circulant, but which is block circulant. And it is block circulant with smaller blocks. So more formally, if we have a polynomial f which belongs to Kn, if we define f0 as being the even coefficients of f and f1 as being the odd coefficients of f, so we are splitting f in two, then the transformation matrix of the morphism which to G, which maps G to f times G, is the matrix given in 5. And we can see that the equation 3 is one particular instantiation of the equation of the matrix representation given in 5. And one interesting remark is that the splitting operation, which is done in equation 4, it's a splitting operation which is also used in the FFT, and this is one of in the fast Fourier transform. And this is one of the reasons why we call our algorithm fast Fourier organization. It's because when you compare our algorithms and the ideas that they use to the fast Fourier transform, you can see that they are very reminiscent of the fast Fourier transform. And something that will be very useful for our purposes is that this change of basis, it's a ring morphism, but it's also an isometry in the sense that if you look at the matrix in equation 3, and if you compare it to the one before, so when you go from this representation to this one, you didn't change at all the geometry of the lattice, because what you've done is permuting some lines, and so it's obvious that if you permute some lines, then you have the same lattice, and we did permute some columns. So when you permute the columns, you do change the lattice, but you don't change the geometry of the lattice. So the gram matrix will stay the same. And that will be very useful for us. Okay, and coming to the fun fact number 3, so distinct morphism of this form, they allow various level of granularity. So for example, we can turn this anticirculant matrix into a fourth anticirculant matrix, but if we use a finer grained level of granularity, then we get a finer grained matrix representation. Okay, so why am I explaining all of this? So what we are going to do in our algorithm is to combine the facts 1, 2, 3. So the first fact is that the GSO is equivalent to the LDL, so we will only work in the LDL. The second fact is that it's easy but tedious to generalize the GSO and the LDL to rings like Kn. And finally, Kn is isomorphic to Kn prime to the power of Nn prime via an isomorphism, which is also an isometry. And so it will preserve the norm, which is good for us. Okay. So in this slide, I will try to explain the intuition of the fast Fourier orthogonalization. So we will start by an anticirculant matrix G. So note that it is already it's already a gram matrix. So it's a self-adjoint in addition to being anticirculant. So we'll break this matrix using the isomorphism that I showed in the previous slide. And then once we have this broken matrix, we are going to orthogonalize it over Kn over 2. So we'll compute its LDL decomposition. And so here we have the matrix L, we have the diagonal matrix D, and we have L star. And then in the step 3, so we are going to store the non-trivial coefficients of L. And this can be stored efficiently since we only have n over 2 coefficients to store. And then we are going to recursively orthogonalize, or rather compute the LDL decomposition of D0 and D1. We are going to recursively apply the steps 1 and 2 to these two elements. So now a few words about the complexity. So the complexity is big O of n log n. So in storage, this is rather obvious because we can show that we have n level of recursions, and at each level of recursions, we will have a big O of n elements. So we'll have at the end big O of n log n elements to store. More precisely, floating point elements to store, because there is no guarantee that the elements in L and in D will be integer. And in practice, they are, when we implement it with floating point operations. There will also be a complexity big O of n log n in computation. So this is less immediate because if we do a trivial, complexity analysis for the computation, we obtain a complexity big O of n log square of n. And this is a bit unsatisfying. And so what we noticed is that instead, so the complexity is due to the fact that we do a bunch of FFT. So each FFT may cost big O of n log n, but since we are doing a lot of them, then it becomes big O of n log square n. But what we notice is that all the operations that we do, they are compatible with the FFT in the sense that they commute with the FFT. And so what this means is that instead of always doing a bunch of FFT, we can simply do one FFT at the beginning, and then we stay in the FFT domain, and all the operations can be done very efficiently in the FFT domain. For example, multiplication, it's linear in the FFT domain, addition too, etc. And so by doing this trick of always staying in FFT, we get a complexity big O of n log n. Okay, so that's for the orthogonalization part. So now, how do we use that in a fast Fourier Universe plane algorithm? So,
Thomas, can I ask a question?
Yes, of course.
About the previous slide?
Yeah.
I guess it's not a precise question, but can you give some idea about how the orthogonalization has to do with the let's say layers of the usual FFT circuits? You know, where you have each layer kind of slowly converting from the power basis to the FFT basis. Is there some way to see what's going on in that perspective?
So the one part where it is very reminiscent of the FFT is when we do that, when we do the splitting operation, so getting from F to F0, F1, this is exactly the same thing as one of the FFT butterflies. And
yes.
So yes, so when we are doing that, it's like a FFT butterfly. So when you go from the left matrix to the right matrix, it's also like you're doing an FFT butterfly, but over matrices. Is that what you wanted to know?
I think my question is perhaps after this step, when you orthogonalize these blocks, is there a way of seeing what's going on where if in parallel you were doing the FFT as well as the orthogonalization? Is that an accurate view of what's happening?
Well, when you orthogonize, I would say that it has nothing to do with the FFT. So yeah, when you orthogonalize, you're just doing LDL over rings. So it's not really related to the FFT. The part where it's related to the FFT is rather when you do this this splitting operation.
Except that the splitting, when you orthogonalize each of these subblocks, you are doing the splitting, right? So it's sort of like you're interleaving the layers of the FFT and the orthogonalization steps.
Yeah, totally. So if you look at step one, the step one is the step where you're doing an FFT butterfly. And the step two, you're just doing a regular LDL. Does it make sense?
Okay, thank you.
You're welcome.
I think so, a bit better.
Okay, cool. So yeah, what we are going to do is that this orthogonalization data is going to be stored in the tree L. So if I'm going to get back to the previous slide, so yeah, when you have this coefficient, it's going to be at the root of the tree, and it's going to be n over 2 coefficients. And then at each recursion, you're going to do the same thing. So that's why you will have 2 children for each node, and each node will have children which will be twice smaller than itself. So that's why the tree is like that. And you can see that you have a tree of n layers, log n layers, and the size of each layer is big O of n. So that's why we have a complexity big O of n log n. Okay, so now I'm going to explain how the fast Fourier nearest plane algorithm on the top of this slide is going to use this tree representation. Okay, so the nearest plane algorithm, the fast Fourier nearest plane is a recursive algorithm too. So in the case where the base field is Q, well, we just apply the vanilla nearest plane algorithm. Otherwise, what we are going to do is that your polynomial, your vector t that you can also view as a polynomial, you will split it in T0 and T1. And because you've done this splitting in a way which allows you to consider T0 and T1 as polynomials of smaller, as element of smaller rings, then you can apply recursively. First, you apply the fast Fourier nearest plane on Z1. Then you're going to use the data L that you have stored during the orthogonalization to you're going to adaptively modify T0 in the same way that you do in the regular nearest plane algorithm. You're going to adaptively modify T0 and you obtain T0 bar, and then you apply the fast Fourier nearest plane on T0 bar. And we showed that this allows you to get something that has the same, to have an output that has the same level of quality than what you get with the nearest plane. So it will give you short vectors, or rather it will give you close vectors with the same level of closeness than what you would obtain with the nearest plane algorithm. Okay.
Does it return, Thomas?
Yes.
Does it return exactly the same answer as the original nearest plane?
No, yeah, good question. So what's going to happen is that if you look, let's look at this. If you look at the nearest plane algorithm, the vanilla one, if you want to apply the vanilla nearest plane algorithm, then what you can do is to orthogonalize the circulant matrix, and what we are going to do is that we are going rather to orthogonalize the matrix on the right. So the vectors will not be in the same order on the left and on the right. So it won't be exactly the same matrix, but in terms of quality, it doesn't make really a difference.
So it is equivalent up to the ordering of the basis vectors in your lattice basis. Is that right?
Yes, exactly.
Okay.
Ordering of the coordinates.
Yes, it will be a reordering of the coordinates in the bit reversal order. And so, yeah, the bit reversal order is already the one which is used in the FFT. So this is yet another common point with the FFT. All right, are there other questions? Okay, so a few comments in terms of efficiency. So our algorithm, we ended up implementing them in the signature scheme Falcon, which is a scheme that with a lot of co-authors I have submitted to the NIST standardization process. And we have in this process, it's better if it's implemented on embedded devices, typically ARM Cortex M4. And the issue is that in this kind of situations, even a storage big O of n log n can become prohibitive, at least for the values of n that we use. So this was problematic. And actually, what we can do is that we can be a bit more clever than that, and we can, instead of computing the fast Fourier orthogonalization in the keygen and the fast Fourier nearest plane, I mean, we use a randomized version of the fast Fourier nearest plane, but you can think about it as this. Instead of doing the fast Fourier nearest plane in the signing procedure and the FFO in the keygen, we do both during the signing procedure. And so what we can do is compute the tree on the fly, and you're going to discard any coefficient of the tree as soon as you don't need it anymore. And if you do that properly, then you can reduce the storage cost to big O of n. So of course, you're going to pay for that because you will increase the computation complexity, but you're just going to increase it by a constant factor. So it's fine. So that's one way where you can gain some complexity in terms of storage. Another way you can do that, and I don't think it's implemented yet, is that you can tweak the operation 2 and make it so that T and V share the same buffer. So essentially, this algorithm, you can transform it in an in-place algorithm where T and V share the same buffer, and so you can gain a little bit of complexity. So you don't gain a factor log n, but you can gain a term big O of n at least. All right. So yeah, that concludes it for the section dedicated to fast Fourier optimization. So if anyone has any question before I move on to the next section. All right. So now I'm going to talk about fast Fourier sampling. And so fast Fourier sampling is just the randomized version of fast Fourier orthogonalization, of fast Fourier nearest plane. So we use the same approach as was first done in the paper by Gentry, Peikert, and Vaikuntha-Nathan, where they introduced trapdoor sampling. Is that in this paper they did take the nearest plane algorithm and mix it with Gaussians to obtain a Gaussian sampler. So in our case, it's the same. So what we do is we take the fast Fourier nearest plane, and for each rounding step, so remember that at the bottom recursion level of the algorithm, okay, at the bottom recursion of the algorithm, we do deterministic rounding. Well, we are going to replace that with Gaussian randomized rounding, and then we obtain a sampler which will sample a point in the lattice, and we can show that it will follow a discrete Gaussian distribution. And so just to mention a few applications of schemes that do actually use fast Fourier sampling. So in Falcon, this is the sampler that we use in the signing procedure. There is also a NetFi proposal for HIB, so hierarchical identity-based encryption, and it's called Latte. And I believe that they also mention fast Fourier sampling as a way to do it, to extract the user keys. And there are also ring signature schemes and group signature which use fast Fourier sampling as a building block in the scheme. So this does raise some practical questions. So the first one is how large should be the Gaussian? And the second one is what about the floating point precision? Because like I said before, it uses a bunch of floating point arithmetic elements on the way. And of course, we have to figure out what is the required precision in order to be able to claim meaningful security. And so we will address both questions with a Renyi divergence analysis. Okay, so what is the Renyi divergence? So the Renyi divergence, it's a cryptographic divergence, and its definition is given by the equation 6. So what is important here is not really the definition of the Renyi divergence, but its properties, because it has a lot of cool properties, and in particular, it has very different properties from the statistical distance, for example. And yeah, so the motivation is we consider a scheme doing Q queries to a distribution DI, and we will not epsilon I the probability of an event that breaks the scheme, and we not epsilon ideal equal 2 to the minus lambda. So what we mean here is that the ideal scheme has lambda bits of security. And what we want is to link the security of the ideal scheme and the security of the real scheme, so with epsilon ideal and epsilon real. And this is given by what are known as probability preservation properties. So with the statistical distance, it's the property given in equation 7. And we can see that it's an additive equation. And this equation imposes essentially, if you want to claim the same security up to losing, let's say, a constant number of security bits, it imposes to take the statistical distance less than 2 to the minus lambda. Okay. So one interesting thing with the Renyi divergence is that instead of having an additive probability preservation property, we got a multiplicative probability preservation property. And that's really nice because we can show that if we take the parameter alpha of the Renyi divergence to be larger than lambda, and if we take the Renyi divergence to be less than 1 plus 1 over q, then we can claim up to a loss of big O of 1 bits of security, we can claim the same security for the ideal scheme and for the real scheme. And actually, the condition on the Renyi divergence is much less strong than the property for the statistical distance, because here we have 2 to the minus lambda, and here we have 1 over q. So what's going on is that whenever you have a search problem and a moderate number of queries, then it makes sense to at least consider doing a security analysis with the Renyi divergence, because it might give you better security claims, in the sense that you will be able to claim the same security, but for weaker parameters. And yeah, I take, for example, number of queries q equal 2 to the 64. And the reason why I consider this number is that if you take a look at NIST call for proposal for post-quantum schemes, they explicitly state that we may consider that the adversary has at most 2 to the 64 queries, so signing queries, for example. Okay, so now let's see how we can use the Renyi divergence for the precision analysis and for the Gaussian standard deviation analysis.
So Thomas, this has been a question. Can you remind us the connection between statistical distance and Renyi divergence? For example, if small statistical distance does imply small Renyi divergence?
If you have a small Renyi divergence, then you do have a small statistical distance, but you don't have the other way, I think. Yeah, okay. I think you can show counterexamples where you have statistical distance arbitrarily small, but Renyi divergence infinite.
I see. So showing a small Renyi divergence between ideal and real is a stronger statement, and that's you get something stronger out of it. Yeah.
Indeed.
Okay, great.
Yeah. And and that's why we cannot always use the Renyi divergence, because there are cases where the Renyi divergence will be infinite. And yeah.
Right.
Yeah. So just one comment regarding what your question. So actually, the Renyi divergence, remember that it's parametric in alpha. And for the case alpha equal 1, the Renyi divergence becomes the Kullback-Leibler divergence. And when you got the Kullback-Leibler divergence, then you can obtain the statistical distance by using a Pinsker inequality.
Right. Thanks.
Okay, so the first application is how do we pick the right standard deviation? So remember that what we do is the same approach that what was done by Gentry, Peikert, and Vaikuntanathan, and later by Peikert in 2010 as well. So we combine a deterministic algorithm with a Gaussian rounding to hopefully obtain a discretized Gaussian of standard deviation sigma. So now there are two conflicting conditions on sigma. So let me explain. If sigma is too small, then there is no guarantee that the output of your algorithm will be distributed as a Gaussian. And in a way, that makes sense because if we were able to say that whatever value of sigma you take, your algorithm will behave like a perfect Gaussian, then it would mean that when sigma goes to 0, then you have a CVP solver. And that would be very surprising. And we can see that indeed, in practice, it's not the case. And so this is not only an issue in correctness, it's an issue in security, because if sigma is too small, well, you can learn the form of the private bases by doing a lot of signing queries. So this was first done by Nguyen and Regev. I mean, in the context of hash dense sign scheme, it was done by Nguyen and Regev, and also later by Duquesne and Nguyen. So this is not an exhaustive list. Okay, so that's one reason why sigma should not be too small. But on the other hand, sigma should not be too big as well, because if it becomes too big, then it means that your trapdoor sampler is going to solve an easy problem. So here, if you look at the number of points that might be sampled by your sampler, here we have 11 points, whereas in the middle case, we have 4 or 5 points that are sampled. So this means that it's easier to forge signatures against a scheme that uses the sample on the right than the sample in the middle. Okay, so we see that you have two conflicting conditions, and what we will seek to do is to find the adequate tools to tell us what is the optimal standard deviation to take. And this is what I will do in the next slide. So here I have a description of the security parameter lambda as a function of the standard deviation sigma. Okay, so remember I said before that you have two conflicting conditions. So the black curve is intended to represent the condition that the larger sigma becomes, the easier it becomes for an adversary to solve the problem. And for that, he only needs to embed the problem as a lattice problem and run BKV on it and solve the problem. And so we can see that it becomes easier and easier. So that's the first condition on sigma. The second condition on sigma is given by a different type of analysis because it's given by a statistical analysis. So ever since the paper by Gentry-Pikert and Vaikuntanathan, there has been theorems which tell us if sigma is large enough, then some distance or some divergence between the output of the sampler and an ideal Gaussian is going to be negligible. And this is nice because then we can use this in security proofs. So in the original analysis by Gentry-Pikert and Vaikuntanathan, it tells us that the security level will be big O or big theta of sigma square. This was refined a bit later in a paper by Vadim, Liu, and I, where we improved the constant, but we still have big O of sigma square. And a few years ago, I've done an analysis with the Renyi divergence, and it gives us something different. It gives us the blue curve, and it tells us that sigma is equal to 1 over q times the exponential of theta of sigma square. So this is nice because instead of having theta of sigma square, then it goes into an exponential. So the price we pay for that is that we have to normalize by 1 over q. And something interesting is that if we don't impose any restriction on q, and in practice, and in effect, it means that q may be as large as 2 to the power of lambda, then the blue equation becomes the same as the previous ones, in the sense that if you say that Q can be 2 to the lambda, then the blue equation will become again big O of sigma square, and we won't gain anything beyond the constant factor. But what's interesting in our case is that we can impose conditions on Q. For example, if we take Falcon and Q equal 2 to the 64, then we will gain 30 bits of security compared to the statistical divergence, because the curve will get higher, and the security that you can claim will be the one where you consider the intersection of your curve with your black curve. Okay, because we know that if sigma is larger than that, it will be vulnerable against BKZ, and if it's smaller than that, then you don't have any theorem to back up your security. And we can see that the blue point will be higher than the points that you obtain with the other types of analysis. Okay, are there any questions? Okay. Okay, so that's for the analysis of the standard deviation. So now I'm going to move on to the precision analysis, and it leverages the same ideas. So we will not ideal the output of the fast Fourier sampling algorithm with infinite precision, and we will not reel the output with finite precision. So again, let's compare a statistical distance analysis and a Renyi divergence analysis. So if we suppose that we have an absolute precision loss of x minus x bar, which would be less than delta, then equation 9 tells us that the statistical distance between the ideal and real distributions will be delta times poly of n. And so this entails the bit precision of lambda plus polylog of n and other stuff. And this is unacceptable in practice, because it would mean that if you need to implement fast Fourier sampling, then you need to implement it with typically multi-precision of 256 bits of security. And this is way too much, and this makes it completely impractical. And under the same condition for a Renyi divergence analysis, we get the equation 10. And there are two interesting things. Is that first, you can see that instead of having a factor delta, we gain a delta square. And this is actually nice for security. This gives us, this allows us down the line to get stronger security claims. So the only thing we pay for that is that you have a factor alpha. And this is also why the parameter alpha should not be too large. But in our case, it will be lambda, the parameter alpha. So if we combine that with the probability preservation inequality of the Renyi divergence, well, it tells us that a bit precision of log lambda q divided by 2 plus polylog of n and other stuff is sufficient to claim a security loss big O of 1. Okay, so this is a summary slide for comparing analysis with the statistical distance and Renyi divergence. So for the evaluating the security as a function of the standard deviation, we can see that instead of having big O of sigma square, we get 1 over q times exponential of big O of sigma square. And for the bit precision, again, we have a much better precision in the case of the Renyi divergence than the statistical distance. Okay, so to conclude, so I would like to present some related works and some open questions. So yeah, this is my own perspective, but some related works are the paper Faster Gaussian Sampling for Trapdoor Lattices with Arbitrary Modulus. So this applies similar ideas to the Micciancio-Peikert framework. So it also does apply a lot of other ideas. What I'm just saying is that if you understood what I said in this talk, then you should be able to understand at least a subset of the ideas presented in these papers, and reciprocally. And another related work is algebraic and Euclidean lattices, optimal lattice reduction and beyond, which apply similar ideas as well as a bunch of other ideas to LLL over two rings. So now a few
Thomas?
Yeah.
Sorry, so I know about the first paper, but can you spell out the authors of the second one?
Yeah. So Kirchner, Espito, and Fuchs.
Thank you.
It's a paper that Thomas Espito presented a few weeks ago at Berkeley, I believe. Yeah, it's this one. Yeah. So a few open questions. So the open question number one is: are there some cryptanalytic applications to the techniques that we described here? So obviously the answer is at least partially yes, because Kirchner, Espito, and Fuchs did it in their paper, where they claim a gain of about 1 million compared to the state of the art or the state of the art of lattice reduction, only for LLL, of course. But of course, an interesting question is, okay, now that we know that we can speed up LLL by a polynomial factor in n, can we also speed up BKZ? So I guess that it's probably doable to, and I'm no expert on that, it's probably doable to speed up by a polynomial factor. But what would be really interesting, and it's probably very hard, is to speed up by more than a polynomial factor in n. So that's the first open question. A second open question is, can we get rid of floating point arithmetic? And there are a few incentives for getting rid of floating point arithmetic. So the first one is that it's a mess to implement, especially if we have to embed it on to implement it on embedded devices. And it's also more complicated from a security point of view, because we have to resort to precision analysis, which can be a bit tedious. And if we have only integer arithmetic, then it will make our life much easier. So one possible solution for doing that is maybe looking at Michanchuk-Piker trapdoors, which work very differently from vanilla GPV trapdoors. So maybe this is one solution where we can do that. And another solution might be to iterate from, so this is a recent paper by Leo Duca and Stephen Galbraith and Yong Yu and myself. So in this paper, we managed to use a sampler proposed by Chris Pikert in 2010. So we managed to instantiate it using only floating point arithmetic. So Chris sampler is what you get when you combine the round-off algorithm with Gaussians. And on the other hand, what we do have in fast Fourier sampling is what you get when you combine some variant of the nearest plane algorithm with Gaussians. So maybe if we take some ideas from this paper and apply it to fast Fourier sampling, then maybe we can make it floating point free. And the last question is, can we implement it in a masked fashion? And this question is partially related to the question 2, because if we can solve 2 efficiently, then it will probably make the open question 3 much easier to solve. But yeah, that's just my take on it. Yeah, so that concludes my talk. So if anyone has question, let me know.
Okay, thank you very much, Thomas. We have several minutes for questions if people have anything they'd like to ask about.
So there is an old question, I think, of Leo. It's on the Q&A, which might have been answered, but worth looking at.
G must be PSD
is referring to one of your early slides.
Yeah.
Positive semi-definite. I think the answer is yes. Is the gram?
Yeah. I think it doesn't work if it's not the case.
Right.
But if G is equal to B times B tilde, then yeah, it's going to be the case.
Let's see. There, any other questions for Thomas? All right. I guess we will finish there. Let's thanks Thomas with for the great talk.
Chris, can I just say one thing?
Yep.
This is Jeffrey. So this is just a format thing. I noticed that when I clicked on the website from Simons, that there was no possibility to ask Q&A. But apparently there are two ways to go from the Simons website. One is through the Zoom, and one just clicking on the the picture where you can you see the slides and hear the speaker, and only through the Zoom you can ask Q&A. So just in case somebody tried to ask questions, but they were signed in the wrong way, just letting you know for the future. All right. Thank you. And now I will clap.
All right.
Thank you.
Thank you very much.
Yeah, may I stop the sharing?